let's go. All right, so today we're gonna do the AP College Physics 1 Unit 6 unit test on Khan Academy. Let's go. It's Monday today. A hoop and a disc with the same mass are released from rest at the top of two identical ramps. The hoop rolls without sliding, and the disc slides down the ramp with no friction. I think you're just gonna have to memorize like a property for this one. I'm pretty sure it was sliding. I could be mistaken though. Alright, nice. Let's go. Second one. The object below is made of interconnected tubes that are hollow throughout. The two identical masses are shown. Which of the following changes in the location of the mass will result in an increase in moment of inertia? So you want it away from the center. Yeah, it's that one. Yeah. Right. A man holding onto two weights close to his body stands on a platform that is freely rotating around. That is not a frictionless axle. His arm. When he raises his arm away from the body, his angular velocity decreases. Alright. Describe why the man's angular velocity decreased. It's because his moment of inertia increased. Moment of inertia increased, resulting in a decrease in angular momentum. Yeah, it's this one, because conservation of angular momentum. Let's go. We're making good pace here. A disc with the rotational inertia that rotates counterclockwise with an angular speed of 10 radians per second. Okay, good. Using SI units. What is the angular momentum of the disc around its center? This is just this two multiplied, right? Right? Is it not? It can't be this easy. I thought it was just this thing multiplied. So it'd be 7.5. Counterclockwise, yeah, it's not a. Yeah, it's positive. It can't be this easy. I'm just gonna. Okay. Wow, that's great. Two discs with the same mass and radius are released from rest at the top of two identical ramps. One disc rolls without slipping, and one slides down with no friction. It's the same property as before, which is the ground first. It's the sliding object, because the other one needs to pick up the speed, and it's rotating around the axle on the ground, and it's like going. Okay, I don't know if you can see my wait, hold up. I'm gonna draw it. Wait, can I draw on this? Draw on the exercise. Yeah. So when you're on the thing, right? Oh, beautiful drawing. And it's like that, and the axle is not here. It's not that. It's actually. Oh, what the. It's actually, bro, I'm not trying to draw a line. Oh my god, it's actually pissing me off. It's this thing, this axle, so it's like so much moment of inertia. Alright, yeah, it's this one. I didn't explain out the other one. A system containing two weights of mass 1/2 m are attached. Ooh, this is good. So this is just m, and this is, so we just add these. Alright, so we're going to do all this in the calculator. Alright, so 1/2 m are attached to the ramp of a uniform cylindrical disc with a radius of 25 centimeters. 25 centimeters is 0.25 meters. Alright, remember that this is the radius, not 25. In 400 grams. Alright, so it's just 400 grams. 0.4. Wait, there's 1,000 in a kilo. So 0.4 times 0.25, but 0.25 squared. Alright, because mr squared is moment of inertia for a point mass. So that's the one of the outer thing. Right. Yes. Okay, I'm not confused here. So then we add the moment of inertia. That's the moment of inertia, the 2-point masses. And then you add the moment of inertia of the disk itself, which is just plus 1/2. We're gonna put parentheses around this because I don't trust it. 1/2 times the mass, which is 0.4 kilograms, times what's the radius, 0.25 squared. Alright, this should be the moment of inertia. And then we just multiply the moment of inertia by the we multiply the moment of inertia by the speed, and it's going 2 revolutions per second, which is 4 pi radians, I think, hopefully. So it's I don't know about this. This is risky. 0.47. Please. Yes! Oh, okay. I assume we did all that right. Okay. Okay, let's go. Wait, what is this? Oh, okay, yeah, no, we just put that in the calculator. Okay, let's go. A plane propeller has a rotational inertia, which is just moment of inertia, of 2 kilograms meters squared. After a clockwise torque of 4 Newton meters was applied to the propeller for 4 seconds, the propeller had a clockwise angular momentum. Okay. So this is just a work problem. Right, yes. Okay. Now this is just torque. Now the work is just torque times the time, right? Yeah, torque times time. It's the rotational equivalent of normal work. Torque times the difference in time. So this is how much the momentum changes. Change in momentum is change in angular momentum, L, is equal to torque times change in time. So we can just figure out the change in momentum, and then we can just we can figure out we'll just start doing it, okay, bro? Alright. I turn the whole thing upside down. Alright, so what's the work applied onto it? It's 16, because 4 times 4. And then what's the angular momentum? It's just 48. Okay, 48. Oh, okay. So 48 minus the initial angular momentum is equal to 16. Yes. Okay, I understand it now. Minus 48. It's 32. Hopefully I did this right. Okay. I'm not. This is dicey. I'm doing math from my head. I'm like actually thinking about physics here. And like the definitions. Okay, if this isn't right, that'd be bad. Oh, okay. Nah, that's crazy. That's fine. But we understood it. It's okay. You have a negative work? That's crazy. Wait, what's like the... What's like the... What's the word for... Angular impulse? Okay, so yeah, impulse is force times time. Yeah, so angular impulse, that's the word. Alright, a figure skater can change her angular velocity W by change, or whatever that symbol is, I just call it W, by changing her arm position. When her arms are stretched out, she has an initial angular velocity of 0.8 revolutions per second. If she pulls her arms in tightly, she changes her initial moment of inertia from that to that. Right. Calculate when her arms are pulled in tightly. Alright. So we just 0.8 times 5.6. That's the angular momentum. And then we just divide it by 1.6, I think. No, wait, 0.8 is in revolutions per second. We have to change that to radians per second. So that times 5.6. That, wait, this is, oh wait, this is in revolutions per second too, so you divide it by, it's okay, bro. Divide it by 1.6. And then divided by 2 times, divided by 2, divided by pi, you get 2.8. Should be right. Good work. Alright. 0.5, and the ball sticks at that. Okay, so this is a perfectly inelastic collision. Alright, so this is pretty easy to calculate, right? What's the thing? Learned this like last chapter, lesson, whatever it's called. 0.15 kilogram ball is thrown with the speed of v is equal to 5 meters per second at a resting stick that can rotate about that. Yeah, so we just calculate the angular velocity, and then the mass. Do we count this mass? I guess we don't. Angular momentum of the ball about this axis. It's just the radius squared. It's just that thing squared times. No need to overcomplicate this, right? 0.25 times 0.15. Oh my. Times 5. By the way, but the 5 here is in linear distance. We have to get into angular linear velocity, we have to get into angular velocity, which means we have to divide it by the radius, which is 0.25, 0.5. Hopefully, we're gonna hope and pray that this is right. Seems about right. 0.38. Please. Yes! Okay. Whew. I did not need to overcomplicate that. What is this? Nah, this is bullshit. Nah, we don't need to talk about this. We can just look at the picture. Nah, this thing. I already saw problems like this, so I know this is going that way, this going that way, this going that way, this going that way. They're all repelling each other. It goes to 0. Alright. Bro, that one question where it's negative. That's crazy. How much did I lose because of that? Nothing. Let's go. Alright, so that's gonna be it. Hope, I don't know what you got from watching me do this. Hopefully some like physics knowledge or something. Alright, see you.